Okay, so we're going to continue work in section 4.3. We were talking about a lot of conditional probabilities and things like that. Now, I've given you in your handout this table and these questions, but I also took a little extra time here to suggest some notation like FP be the result of randomly selecting the individual from this table that was a false positive, or you could have somebody that was negative. So that'd be another possibility. Likewise, we had people that tested positive. So P is the event that you test positive as a randomly selected individual from this table. And last but not least, there's event C, which means you actually have hepatitis C and that you're randomly selected from this table. Now, one of the things I want to go over a little bit more with you is some notation. And some of the notation I can use would look like this, N bar. Now, on the exam, some people got a little bit confused, understandably so, that meant the average of something somehow. It's not. This is set notation. It's referring back to event N, but it doesn't mean that we're randomly selecting somebody who tested negative. It's the complement of that event. So in words, what would the complement of this event be? Anyone?
Like the chance that, like if something was the chance that it would happen, it'd be the chance that it wouldn't happen.
Yeah, so in words, if N is the event that they tested negative, what's N bar?
That's positive?
Yeah, they tested positive. Perfect. So they tested positive. So really, you know, I didn't necessarily have to use this notation P, but it just felt a little awkward somehow to write down, you know, probability of P. Although that's what my other two classes preferred. They wanted to look at the probability of P. Another way to say P in this scheme of things is to call that N bar. So P and N bar really mean the same thing when we're talking about this set of data. They're equivalent. Let me put 3 equal signs there. These are equivalent, P and N bar. So I'm not sure about you guys, but I'm just going to make kind of an executive decision here. And let's go with the probability of P. So it's kind of weird. You got P for probability and P for positive, but we'll make it work. We want to look at the probability of randomly selecting somebody from this table that test positive. So what is that? Let's go back up to our table and try and understand that a little bit more. One thing I'm going to do is put down some marginal totals. So that would be 337 here, and then 1163 here, for a total of 1,500 people that were tested to make the data for this table. Let's do the marginal totals across the rows then. This would be 345, and this would be 1155. A nice double check of your work is that the row totals total down to 1,500, and the column totals total across to 1,500. That is, they both should total to the same thing, and they do. So we're going to start with this right here, probability of P. What's the probability that somebody tests positive? Well, let's look back at the table. First of all, how many people are there in this data set or in this table?
1,500.
1,500. So that's actually going to be our denominator, 1,500. Now in the numerator goes the number of successes. And for us in this case, that's the number of people that tested positive. So How many people tested positive here?
337.
337, and that's great. Now, it's tempting to say 335, but 335 are the people that tested positive and had hepatitis C. Then you have 2 more that didn't have it, but also tested positive. So these would be what we consider the false positives, FP, down here. But that's not what I'm interested in here right now. At least not yet. Let's actually take a closer look at problem number 17 here. It says, find the probability of selecting a subject with a positive test given that the subject does not have hepatitis C. So, okay. Let's see if we can. Did I read that right? Given that the subject does not have hepatitis C. So, okay. Probability of a positive test given, now we got to be kind of careful on this. There's 2 probabilities that I want to eventually calculate. I want to get the probability that somebody has a positive test given that they have the disease, given that the selected individual has hepatitis C. So that's one probability, but that's not what I'm looking for here. I want the probability of a positive test given that they don't have the disease. So what notation should I use here? Can anyone tell me?
Would it be FP for false positive?
That's actually not a bad guess. But we don't have to work too much harder than what we did here. So that's kind of a hint.
Is it C bar?
C, would it be C?
C bar.
C bar, good. Probability that they have a positive test given that they don't have hepatitis C. Now, just to kind of refresh you a little bit here, let me do this. So this box kind of represents your universe, or we call it our sample space. So this is everything that can happen. If this is event A is what's in that circle, then A bar is everything else. It's everything outside that circle. So your heads or your tails, you won the election or you lost, you rolled a 6 or you didn't roll a 6, but you're one or the other. So you have hepatitis or you don't have hepatitis. There's no in between. So that's what we have here, is the probability that somebody doesn't have hepatitis C, or excuse me, probability that somebody tested positive, even though they don't have hepatitis C. Let's start with this one. Probability that they test positive, given that they have hepatitis C. What's that going to be? Well, this changes things. I'm telling you some extra information. So we're no longer going to look at the entire table. We're no longer going to look at the samples, the entire sample space. The entire sample space is this table. By telling you that we have hepatitis C, I'm really saying we're right here. We're looking at somebody who has hepatitis C. So instead of 1,500 people in my table, how many people do I have as my new sample space, so to say?
345.
345. And of those, how many had a positive result?
335.
335. Good. So 335 out of 345. That would be this conditional probability down here. 335 out of 345. Okay. How about this other one? Oh, before I do that, are we okay with this one? By telling you this extra information, what I've really done is I've changed my sample space. Instead of it being the whole thing, I'm like, okay, no, we're just in here. Instead of it being the whole table, we're just someplace on the first row. 335, that's the positive test results amongst those who had Hep C out of the total people who had Hep C. Let's look at this next one. Probability that they test positive given that they don't have hepatitis C. So these would actually be the false positives. So let's keep in mind this part here, C bar. You don't have hepatitis C. Where does that put us on this table?
The second row with no hepatitis C.
Perfect. Thanks, Megan. Now we're right here. The second row amongst the people that don't have hepatitis C. So someone else now, pick up the thread here. What's the probability that you don't have, or that you have a positive test given that you don't have hepatitis C? So we're on this row. What's the probability of a positive test for people on that row?
2 out of 1155.
Thank you, Jess. 2 out of 1155. 2 out of 1155. Beautiful. Now let me throw in some percentages here for us, just so that makes this a little bit more clear. This percentage is about 22.5, 0.225. This one, man, that's got to be pretty close to 97%, so it'd be 97.1%. And this is less than 1%, 0.0017, so 0.17%. Now I point that out because I want you to see something about these probabilities. The initial probability for a positive test was about 22.5%. That's for the whole table. But if I tell you something about whether or not they actually have hepatitis C or don't, that changed this probability, didn't it? If I tell you somebody has hepatitis C, you're going to estimate their probability of having it, a positive test, much higher. Look, it jumped from 0.225 to 0.971. If I tell you they don't have hepatitis C, are you going to be betting the house that they do have a positive test? I hope not. That's a very small probability. And that's good because these would be false positives. They have a positive test even though they don't have it. So that's a pretty small probability. Now, Marty Triola, the author of your book, is usually really good at getting actual data. I don't know if this represents actual data or not, but these are really good. But keep in mind, even as good as they are, when you start applying these to millions of people, there's still going to be a lot of false positives and false negatives. There's a couple things that can go wrong here, so you have to be very careful with these kinds of results. But that's the epidemiology side here. I want to look at the probability side. Because when I told you something about whether or not the patient actually had hepatitis C, it changed that probability. So this event and this event are linked. They're not independent. Knowledge of this one affects the probability of this one. So that means P and C are dependent events. That's another little takeaway from this example. P and C are dependent events. Okay. How are we looking with problem number 18 there? or 17, I guess I should say. 18 is coming up. And for problem number 18, we're going to do kind of the reverse here a little bit. We're going to start by looking at the probability of a negative test. And there's a couple ways you can do this. You can do 1 minus the probability of a positive test. There's nothing wrong with that. That'd be 1 minus this probability that we already calculated. 337 over 1500. And then I can get a common denominator here. So that'd be 1500 over 1500 minus 337 over 1500. Or 1163 over 1500. So that's the probability of another test. Is there a different way I can get this number or make sense of this number? Anyone see it?
The negative result.
Yeah. There's 1,163 negative results out of 1,500 people tested. Simple. It's actually probably easier to calculate it directly as opposed to using the complement rule. But it's just a good practice problem for the complement rule. Okay. Do I expect you to calculate this way in a test? No. I'd probably calculate it directly off the table rather than the complement rule. That's just me. But in paralleling what we did just a minute ago, I want to look at 2 more probabilities. I want to look at the probability that somebody tested negative, given that they have hepatitis C. And at the same time, I also want to look at the next probability that they test negative, given what? Can anyone make a prediction here? What am I going to write here?
They don't have hepatitis C.
Good. They don't have hepatitis C. So take a minute, look at the table, and see if you can't come up with these 2 probabilities. Now, the thing is, with each of these probabilities, you're restricting your sample space. So you're not going to be looking at the whole table anymore. You're just going to be looking at part of it. So take a few seconds, then maybe we can get some volunteers here to try and help fill in these probabilities. So Hannah, let's look at this probability of n given c. Where are we at on this table? What should I focus my attention on?
Hepatitis C.
Yeah, so this row, the people that just have hepatitis C. So there's 345 of them. How many have a negative result?
10.
10. So 10 out of 345. Cool. Thank you. Let's try somebody else here. Aiden. Let's take a look at the second one. Probability of a negative result given that they don't have hepatitis C. Where are we at on the table now?
That would still be in the negative test result, but it would be in the column of no hepatitis C, meaning that the value would be 1,153 over the 1,500 total.
Actually, you're pretty close. So by telling you that you have no hepatitis C, we're actually on this row. This is the row that has no hepatitis C. So there's 1,155 people here. So let's put that down as our denominator. 1155. Well, let's look back together. Amongst these people, the 1155, how many tested negative? And that'd be the 1153 that you stated. So 1153. Cool. Are we okay with these two calculations here? Those two probabilities? All right.
Is it possible to do another one? I think I've had them flipped.
We're gonna do two. We're gonna do 2 or 3 more.
Okay.
We'll probably do 2 more, and then we'll go back and do kind of like a probability of A or B type problem out of this. So yeah, we're gonna do a couple more. Yes. Now let's take a look here, and we'll throw on some numbers. So let's take a look. 1163 divided by 1500. That gives me about 77.5%. So not quite 78% of people tested negative. But if I tell you that somebody actually has hepatitis C, and I ask for the probability that they test negative, then that probability drops, and it's about 0.029. So about 2.9%. But if I tell you they don't have hepatitis C and ask you what's the probability that they test negative, now it's going to be virtually like 99%, I would imagine. Let me just do the calculation here. Whoops. Might help if I could type it in correctly. 155. There you go. So about 0.998. Wow. So does knowing whether or not somebody has hepatitis C affect what we think about their probability of testing negative?
Yeah.
Yeah, absolutely. If I whisper in your ear, they do or they don't have hepatitis C, that's going to drastically change your opinion of this probability. So you have this probability, and this probability. Knowledge of C changes that. So my question to you, are events N and C independent?
No.
No, they're not. N and C are dependent events. Yeah, because the outcome of one changes the probability of the other one. Whether or not you have hepatitis C certainly changes the probability that you'll have a negative test result. Yay. But let's flip things around. I kind of sense that there's some interest in seeing another example like this, and I'm going to give you 2 more. 2 more examples like this. So, anything on this one before I move on from it, though? Okay. Let's try a different one. Let's try probability of C given N. Well, that changes things. So what am I telling you? Before we do our probability, I'm telling you something. What am I telling you before we do our probability? What do you know in advance? What's this telling me?
The person is negative.
Thank you, Megan. Person tested negative. So if the person tested negative, are we dealing with this whole table anymore? No. So Megan's helped us out with the first part. Someone else pick up the ball. What part of this table am I dealing with? I'm just dealing with a portion of the table now.
Just the negative
The right
side.
side.
Yes, well done, both of you. The right side. So now we're dealing with this, and my denominator, whatever else is going to go on, my denominator is going to be my 1163, because that's all I've got. What's the probability that you have hepatitis C if you got a negative result?
10.
So 10 goes in the numerator. You have 10 negative results amongst the people who have hepatitis C. So 10 over 1163. Let's compare that to this, the probability of C. Now, did I give you any extra information here? No. So what's going to be my denominator for this one?
1500.
Nice, 1500. Because you're dealing with the whole table. I didn't tell you, oh, we're just dealing with people who have hepatitis C. Oh, we're just dealing with people who have negative results. It's the whole table. And of these, how many people had the hepatitis C?
345.
345. The marginal total, not just those that tested positive, but everybody. So 345 out of 1,500. Now that's exactly 33%. This one, you gotta pull out a calculator for, but it's about 0.0086%, or 0.0086 is the probability, or 0.86%, less than 1% chance. Do you know what question's coming up next? Our events C and N, what? Independent. What do you think? Are these just independent events? Or does the outcome of one affect the probability of the other? Yeah, I think knowing that somebody tested negative certainly affects the probability that they have hepatitis C. You could also do probability of C given N bar. You can look at that one. What's another way to say N bar?
Positive.
Yeah, positive. So if I wanted to, I could just say, you know what? What's the probability that they tested, or if they tested positive, what's the probability that they actually do have hepatitis C? So we have to look at a different part of the table. What would be my denominator for this current probability? How many people tested positive?
337.
337. And of those people that tested positive, how many actually had hepatitis C?
335.
335. So again, whether or not they're positive or negative, that information greatly impacts the probability of them actually having hepatitis C. So that's going to be like 99%. Mm, 335 divided by 337. Yeah, so about 99.4%. Back to the question here, though. Are these events independent?
No.
No, because this probability was changed by knowing whether or not you tested positive or negative. It drastically changes the probability. So answer is no. All right. Now it's time to give you an example for contrast so that you can have a better idea of, well, why are we looking at this independent stuff at all? It seems like everything is dependent. Let me give you a different example. Let's, I don't know, I'll just call this example D, just to have a label for it. But let's let H1 be the event of a head on the first flip of a coin. So you're tossing a coin, you get a head on the first flip. H2 is going to be the event of a head on the second flip. And now what I want to do is I want to look at my sample space. So let's look at our sample space. This is the space of all things that can happen. Now, on the first flip, I could flip ahead, and then a second flip, I could flip ahead. Or I could start out with a head and then do a tail. Or I could start out with a tail and get a head, or start out with a tail and get another tail. But those are the 4 points that go into the calculation or that go into my sample space. So that's it. That whole thing is my sample space. Now, it's important in terms of calculations that each of these events is equally likely. And that's only true because we're going to assume that we have a fair coin, that probability of heads and tails is the same thing. So all 4 events are equally likely. There you go. Let's calculate some probabilities. We'll start with the probability of H2. So, okay. Because these are all equally likely, and that's not going to happen with every sample space, but because these are all equally likely, we can just count up, for instance, that there's 4 possibilities there. That's the number of points in our sample space. There's 4 of them. But of those 4, how many represent a heads on the second flip?
2.
2. Thank you. And that reduces this down to 1/2. There's a 50% chance that you'll get a head on the second flip. All right. But now I'm going to tell you something ahead of time. Before you flip that coin the second time, I'm going to tell you, psst, hey, we got a head on the first flip. Now that changes things. Instead of working with the whole sample space, now we're just working with that part of it. We just have that little bit. So, okay. So our sample space has been reduced from 4 down to 2. How many ways are there in our new sample space? How many ways are there to get a head on the second flip?
1.
1, 2.
Well, that's a head on the second flip, that's a tail on the second flip. So there's really only one way out of the 2 points in my sample space that you can get a head on the second flip. So, wow. Did knowing what happened with H1 affect the probability of H2?
No.
No, it's still 50-50, right? So what happened in the past doesn't affect this at all. What's that saying about H1 and H2?
They're independent.
Excellent. H1 and H2 are independent events. What happens with one does not affect the probability of what happens with the other one. They just are independent. Now, this is actually the root of a problem called the gambler's ruin. A lot of times gamblers lose track of this independence. You're at a slot machine, you keep on pulling the handle, you've been pulling it for hours, and you're like, it's due, it's gotta hit, it's gotta hit, I know it's due. But you know what? Each pull of the handle is independent from the previous pulls. So whatever probability there is of winning doesn't change. Your probability of winning on this pull is the same as on the previous pull. And if you've gone 100 times in a row without a winner, your probability of winning on this next one isn't any different than it was beforehand. It's just not. And a lot of people are like, no, it's due, it's due. These devices, dice, roulette wheels, slot machines, they don't have a memory chip saying, oh, you know what, this poor guy's been out here forever. I'll come up with a winner. They don't. They're independent. So if these probabilities are the same, then they're independent. But when knowledge of that second event changes the probability, so probability of hepatitis C was 0.33, but if I know if somebody tests positive or somebody tests positive or negative, that changes the probability of having hepatitis C. That means they're dependent. Those probabilities don't change, they're independent. So I'm hoping that that's helping drive home the point of dependence versus independence a little bit. Now we'll do one more from this table. It's problem number 19. But let me give you a chance to, you know, ask for some more clarification where you need it. Doing okay there? Three, two, one, sold. Okay, let's look at one last one here from this table. And it's going to be problem number 19. Find the positive predicted value. Now, one of my students this morning was like really worried. He's like, are we going to have to know what positive predicted value is? No, no, you don't. And in fact, it's actually defined for you here in the problem. They tell you what the positive predictive value is. It says, find the probability that a subject has hepatitis C given that the test yields a positive result. Actually, I think we already calculated this, right? All right. So I think, didn't I just calculate that one?
I think the one you're thinking about is we just tested the probability that they have hepatitis C, not that they tested positive and have it.
Okay. Well, tell you what, let's see if we can't frame this in terms of these letters that I used here. So, yeah, actually, you know what? We actually did calculate this one.
Yeah, that was one of our first ones. Whoops.
So, so I threw this in as kind of like a bonus for problem number 18. I probably shouldn't have. Find the probability of a positive predictive value for the test. That is probably that they have hepatitis C given that they have a positive test result. So what they're doing is they're telling you, okay, you've got a positive result. Now what's the probability that you have hepatitis C? And we did calculate that one. It was what, 0.994? Let's see, it was 335 over 337. So pretty high. It's got a good predictive value. But that's going to mean you're going to miss a few people, 6 out of every 1,000. And when you're talking about 1 million people, now that's going to start adding up. So, but none of these tests are perfect. Trying to see, is there a way I can nurse this one more out of this? Yeah, let me give you some more practice in something that I didn't put on the last test, at least for credit, and that is this one. So we'll do a bonus problem of probability of C or N. Now this is getting away from conditional probabilities, but we're still going to work with the same table. The thing that you need to keep in mind about these, addition rules is you can kind of just do them like this, split it up. Probability of C plus the probability of N minus the probability of their intersection. So let's look at this one as kind of a wrap up from this section. Probability of C and probability of N. Are we looking at the whole table or part of the table when we look at these two probabilities?
The whole table?
The whole table. Thank you, sir. The whole table. So you're looking at all 1,500. So our denominator should be 1,500 for both of these. Now for the first part, I want the probability that they test, or excuse me, that they have hepatitis C. So, okay. Some more voices here. Some different voices. What's the probability of C?
345 over
300.
1,500.
Good. 345 over 1,500. Excellent. Some more new voices. What's P of N? Hmm.
1,163.
Good. Over 1,500. Now this last one is still going to be over 1,500. What happens is that if you calculate the probability that somebody has hepatitis C and then the probability that somebody tests negative, this gets double counted twice, or it gets counted twice, double counted. So we'll subtract it off once. And what you're going to do is you're going to subtract off the probability of P and C. So that's people who have hepatitis C and tested negative. How many of those are there in this table?
2.
10.
10.
2 or 10 have hepatitis C and tested negative.
10.
10.
10.
10. So overall, if you add this up, I think you're going to get 1,498 out of 1,500. So if you're looking for somebody that tested negative or has hepatitis C, that's virtually everybody. The only people that you're leaving out there are the false positives. There was 2 false positives there, essentially is what you're leaving out. Okay. How are we looking on that one?
Pretty good.
All right. Let's call it a wrap then for section 4.3.